All right, so I'll get started. I'm giving a guest lecture today on, well, a variety of kind of data-centric language modeling topics that I hope you will find useful. I know you all have been learning about kind of grounding and hallucination, and hopefully some of this will be of interest in thinking about those things. So kind of the starting point for this is thinking about where do language models' sort of remarkable capabilities come from, right? I think many of you actually maybe started in the post-LLM era in this field. So like this is just all natural to you. It's like, of course, language models can do all the things. But this is actually pretty surprising to many of us who started in the field way long before that. And so it's kind of amazing that all of these, different NLP tasks can just get shoved into a language model in sequence-to-sequence form, and they can do well. I put T5 up here because it's one of the earliest models that really did some of this. And then, below that, if you look at kind of what does real-world usage of a chatbot really look like, it's incredibly varied. The second plot here is from LMSys1M, which is a pretty cool resource. It's from the Berkeley folks that run Chatbot Arena. They went and then they analyzed like what do people use chatbots for? And they found all sorts of different things like discussing software errors and solutions, and like creating business strategies. I don't know if I trust my LMs with that, and some stuff that's a little bit less safe for work. Maybe surprisingly, there isn't like a homework help category, but you can kind of see all sorts of different things that people are asking for help with from a language model. And I think the reason why LMs do so well is because they're trained on incredibly large amounts of data, right? Pre-training data is incredibly varied. It's a huge slice of the internet, and on the internet, people are doing lots of different things, right? So because of that, we get great generalization, but at the same time, we know these systems don't really do well everywhere, right? That's the whole point of trying to understand and improve LM chatbots. So, there have been really nice studies. This one's by some folks at UW showing that language models really struggle on niche entities. What's kind of an interesting fact is, on really, really popular entities, like the ones to the right here, this is measured by, I think, like page accesses on Wikipedia or something. These models are really good. In fact, they're better than even a retrieval augmented system, which is kind of surprising. So you might as well just ask the language model directly. But as these entities get less and less popular, as you go to the left of this plot, your unassisted language model just does worse and worse, and retrieval augmentation starts to do better, right? So there's a pretty clear correlation between the popularity of entities and how well these models do. And so that might make you think about, the pre-training data. What are people building the LMs really interested in? So if you go to, I don't know, Anthropic, OpenAI or something, and you talk to those folks and you're like, what are you really excited about? They're going to be talking about like, oh, cutting edge knowledge. We want our language model to do like, I don't know, quantum physics. We want it to be able to like, make the next generation of language models themselves. Yes?
How can retrieval augmentation harm the language model's performance?
Yeah, like if you put irrelevant contexts in, you can certainly harm the performance of the model. You might also retrieve, some misleading but correct-looking things and put them into the context. It's not really always the case, especially for like really, really obvious facts, that retrieval augmentation is a big win, right? Like I don't need retrieval augmentation to know that the Earth is round. Going back to kind of cutting-edge knowledge, so there's a lot of interest in trying to develop language models that can do really well on scientific knowledge that's rare on the internet, right? And finally, if you're thinking about bias and fairness, right, we know that these models do not do well, uniformly across the globe. As people who, speak and interact in English, we are very much privileged to be able to take advantage of an incredible amount of high resource, English languages on the internet, which makes these models really, really good at English, right? But on the other hand, if you're operating in much lower resource languages, these models do much, much worse, right? So why am I bringing up these three different examples? They really all come back to the data, right? Like the pre-training data, at some sense, drives base model capabilities. In turn, base model capabilities derive your instruction-tuned model capabilities. And if you're building a system on top of it, it's going to really affect those as well, right? So it all kind of comes back down to what's in the pre-training set of your language model. So I think, I don't know how many of you have tried to build your own language model or have looked at a language model pre-training data set. But one exercise that I'm going to go through now is to, say, let's think about the pre-training data. Like, what does that look like, right? So I think if you have like a kind of naive view of what pre-training data looks like, I think it looks a little bit like this on the slide right now. So on the left, this is pre-training. And pre-training is nice and clean, and it's like Stack Exchange. It's stuff that you can read. It's high quality stuff. On the right, you're going to evaluate it, and this is a very badly named eval called human eval that everyone uses for code evaluation. It's something like, oh, here's a function, here's an instruction in comments. Now synthesize this Python code on the bottom, right? And in many ways, there's a good alignment between the left and the right. On the left, you've got this like QA format, you've got some code in the middle, and if I like transform this a little bit, you can imagine that it's kind of similar to the evaluation, right? There's good overlap between the two. And so I think this leads lots of people to say like, oh yeah, of course language models work, pre-training data covers everything, and it's very similar to evaluation data. But really, pre-training data, the vast majority of it, if you take a random web scrape, looks nothing like your evaluation data. As part of a course that I was teaching last spring, we went through an exercise of just picking a random page from Common Crawl. And so this is the first page in one particular Common Crawl dump called 000-84smartcode.com. And what is it? It's as far as I can tell, it's blog spam. It's just talking about, it has random outbound links. It's talking about test prep training. I think it has no real knowledge content value in this thing. And so the vast majority of the web, if you do not filter it in an intelligent way, looks like this. And if you train your models on this, I mean, you can easily imagine the model is going to behave very badly, but also you've wasted very, very precious resource, which is your pre-training compute, right? And so for all of these reasons, there is a lot of interest in thinking about how do we select and curate the data on which our models are trained, right? Because that's the foundation of all of the knowledge and all the things that these models have, right? So I'll talk about that first. The other thing I want to talk about is kind of this knowledge gap for lower resource domains. So we know that as entity popularity goes down, language models do worse, right? This is just kind of a fact that's been observed over and over. And so, can we somehow overcome this gap? I have some knowledge out in this tail that I really want the language model to understand at like a deep, fundamental level. Is there a way to do that? And so, there's some questions about whether that's possible. And I think in a way, this is a very interesting question. I'm going to approach it much more from the basic science, like, is it possible to do X or Y kind of perspective? But I think it's related to very important, broader concerns in language modeling. On the left, if you're much more of like I want to build applications, I care about applications in the outside world, then this left figure may be of interest to you. It's some folks who are, analyzing the progress of AI, sort of, arguing that really public data, there isn't that much of it. It's going to get rapidly used to train language models. Really, the next stage of value really comes from, proprietary data like, chat logs inside a company, internal wikis, like all those things are very important and valuable in building the next generation of AI systems. On the right here, this is a really kind of fun article, I'll call it, from Epoch AI, where they were asking the question like, in what year will we run out of LLM pre-training data given the rate of current progress, right? And that's kind of almost a ridiculous thing to ask about because there's a lot of data on the internet. But as I said before, there isn't that much high quality data on the internet, right? And so the internet data that we train on for language modeling is actually quite a precious resource. And if you think about it, the compute being used to train these models, is scaling up very rapidly, both from investment, like people are buying bigger clusters, but also NVIDIA is just making faster and faster GPUs, right? And so the blue line is kind of a projection of how many tokens, different model runs use. And, their argument is like roughly somewhere around 2030, we're just gonna like exhaust all the tokens on the available internet, right? And so if that's kind of the future, then you really start to care about, okay, how can we more data efficiently train models? That's a very fundamental question to continue progress in building future language models. So the approach in this talk is going to be just like a very simple, very direct way of thinking about these problems, right? I'm not going to give you like a deep algorithmic innovation. I'm going to play it safe. And what I'm going to do is I'm going to use the current existing very effective paradigm. And what is that? That's just pre-training big language models at scale. We know that works. I'm not going to change that, right? But I'm going to try to combine that with some very simple ideas to try to break or to improve upon those two things that I talked about before. The first one being, how do we select good data? The second one being, can we train models more data efficiently when we don't have that many documents? So this is based on some two recent works that I'm excited about. The details of the work may be less important, but they have some fun ideas that hopefully you'll take away and kind of enjoy thinking about, right? So the first part of this is going to be talking about data selection. How do we select good data for pre-training in a way that will give us more capable, better models? So let's get started with thinking about data selection. Like, why does data selection matter? I can make my own arguments, but I think it would be maybe more credible to let a frontier lab training big language models do the talking for me, right? So you can go download and look at the Llama 3 tech report, and they're pretty upfront about what's important or what they thought was important in training the biggest, most capable open source models at the time, right? And they say, okay, there's three things that are important. There's data, there's scaling, and then there's an attention to detail in the engineering, right? It's not necessarily like deep algorithmic innovation, which saddens me as a researcher, but really, of these three, right, scaling is really just like get more GPUs and do the systems engineering necessary to orchestrate those. And attention to detail is, train your models in ways that don't blow up. But really, so then the variable component, the part that's, at least to me, most mysterious is this data thing, right? Of the three sort of pillars, data is the most unknown. So, but also at the same time, data is something that's incredibly opaque. And this is partially due to the current, crop, I would say, of copyright lawsuits that have targeted every foundation model training lab in existence. But if you look at, for example, the Llama 3.1 report, they will say, they have pre-trained from a variety of data sources. And I'm sure many of you have seen kind of this viral video of former CTO Mira Murati, in an interview. The interviewer asks her, like, so what did you train your video generation models? And she's like, publicly available data, right? This is the kind of situation we're in. None of the labs like to talk about what data they use. And so it's very much a mystery, I think, to almost everyone working in the field, what the exact training data is. So there has been some work trying to open source replicate data pipelines and to train highly effective models. And I'll talk about one example as I continue through this talk called DataCompLM, right? And DataCompLM was this attempt by some folks at Apple and Toyota Research Institute to basically build a full pre-training filtering pipeline that results in an effective model. And they end up training a pretty reasonable 7 billion parameter model. And the one thing to take away from this figure on the bottom here is it's a pretty complex hand-engineered pipeline. You've got like English filtering, you've got page length filtering, repetition filtering, deduplication, this algorithmic filter that I'll talk about in a moment, and then you select about 1.4% of your original, I think they start with like 200, 300 trillion tokens, all the way down to a couple trillion tokens at the end, right? So this is a really highly engineered data filter that you get. And so, okay, so you take a look at this and you're like, all right, there's a highly effective data pipeline. I would like to understand, like, what is the state of the art? And so if you look at the state of the art, in some ways it is deeply disappointing because the best performing algorithmic data filtering pipeline right now is a bigram classifier that attempts to distinguish websites, random websites on the internet from Reddit's Explain Like I'm 5 subreddit and a instruction tuning data set called Open Hermes, right? And it is kind of, doubtless that this pipeline works. Like the model that they trained is good. But this seems totally ad hoc and arbitrary, and it is deeply dissatisfying to me as a researcher that some random subreddit is a core component of a data filtering pipeline, right? And so one thing that I would like to understand is, are there simple principled alternatives? Are there some principled approaches to classifying based on bigrams. Like that would be cool, right? And so here is the simple game that we will play. The inputs are a target benchmark. This is the thing I would like to do well on. The token count. This is the size of my data set. And then the pre-training pool. This is the pool of data that I can filter from. And then the output of the algorithm that I'll present is going to be a data filtering policy. This is a method by which I can filter my big pool and get a much smaller pre-training data set that I can train my language model, right? So that's kind of the name of the game here. And we are far from the first ones to think this, right? Like it is kind of an obvious thing to want to have an algorithmic way to select data to make your models better. This is like kind of a foundational question in machine learning. Many people have tried. The results have been deeply mixed. I'll talk about some ideas that maybe you'll enjoy hearing about and have been sort of classic at this point. One approach called data models has been proposed by some folks at MIT. And this is a very, very simple idea. It says, okay, I want to understand what good data looks like. Let me train a bunch of different models, removing data on each one, and then let me build a big regression model that goes from which data was included to what my downstream performance was, right? Like a very simple, let's just make a big regression model approach. Some folks here, Percy, who's upstairs here, and others proposed influence functions, and you can think about this kind of as a Taylor approximation to how the model trains, right? We can't reason possibly about how changing one piece of training data affects the whole training process, but maybe we can reason about small perturbations in like upweighting or downweighting data points and how that might affect my final model, right? So I'm really glossing over the details of like the influence function style things, but you can just kind of think of it as like a Taylor approximation. And there's been many others that try to use like robust optimization or similarity, like n-gram overlap of data points. Basically, if you have an idea, probably someone's thought about something related to that, because this is a big community where everyone's tried all sorts of different things. And so this is an area with a lot of different ideas, but I think the really sad reality, and one of the things that I think I've been kind of sad about here, is none of this has really moved the needle on how you actually train language models. Like there's a lot of algorithms, but basically every study that has run data selection at scale has basically found like, oh, maybe actually just like pick randomly at uniform does the best. That's this paper by NVIDIA. Or the handcrafted Reddit subreddit classifier from Datacomp. Those were the kind of best performing things that people had found, right? And so empirically, none of these algorithms have moved the needle, and that's been very saddening for me. And so let's think about why algorithmic data selection has remained so elusive and so hard. Well, there's a cost reason, right? If you want to understand how data affects a language model, well, you have to at some point, like remove data and train a language model, right? Like that's the only way to really know whether you're right or wrong. And that's an incredibly expensive endeavor. Another thing is, really, you can only do this thing, this counterfactual, 10 to 50 times, because I can't train that many language models. It's hard to get a lot of data, right? And so this has led to a huge number of problems. And so let me just walk you through why this is like such a difficult thing for a long time. Let's say your goal, right? Like you've been put in charge of, I don't know what organization would be training 7B models now. I don't know. Let's say you've been put in charge of like a new team at Google or something, and you're going to be training a new 7 billion parameter language model, right? And your marching orders are you got to do well on MMLU, which is a question answering benchmark, right? So that's your goal. So how are we going to do that? How are we going to select data to do well on the task? Well, if I want to use something like data models to do this, right? So this is the hypothetical. I'm going to train 1,000 different small models, each one with a different data mix. And then I'm going to measure how well each of these models do. And then I'm going to build a regression model that goes from what the data mixture was for each of these 1,000 models to the downstream performance. And once I have this regression model, I can find the best possible mixture and I can train on that, right? Very conceptually simple, incredibly expensive, and totally practical in practice, because the cost is to train 1,000 different models, and I can't really train more than I can't estimate more than weights for 1,000 domains. So that seems pretty rough. Okay, wait, there we go. Okay, so there's this fun idea that I and a couple of others have been working on for a bit, the last couple months. The field moves fast, which is actually whenever you want to like analyze a model or like think about the behavior of a model, don't ever train your own model. All we're going to do is we're going to download a whole bunch of models from Hugging Face, right? Like there's a lot of collective resources and intelligence that has been used to train, at this point, over 100 high-performance models that are now publicly available, right? It seems very silly for me to spend my own money to train my own model when so many high-performance models are already available. And so, if I can use these publicly available models, understand these models in a deep way to try to, understand the relationship between training data and downstream performance, then maybe I have a way of understanding data kind of at scale, right? So the advantages here are no cost. It's just downloading models. It's heterogeneous. There's coding models, there's multilingual models, there's all sorts of different models on the internet. And then, I have 100 different models, especially trained at scale. That's a decent number of data points, right? So the only issue here is what I said before. No one wants to talk about what they trained on, right? Like none of these 100 models that I can download, almost none of them, that I can download on Hugging Face have publicly available pre-training data, out there for me to look at. So that seems really hard because what I want to understand is how pre-training data affects model performance. How can I do that if I don't know what these models trained on? So really the fun little trick here, this is the one trick in this talk, which is it turns out you don't need to know what these models trained on. Because there are things that we can measure just by using the parameters of these models. And in particular, the thing that we can measure is the loss of these models, right? So what I'm going to do is I'm going to take these publicly available models, and I'm going to measure how well they compress text, or what loss they get, what their log likelihoods are on different pre-training websites, right? And so a model, might fit this website better. This other model might fit this other website better. And I'll have this big matrix where the rows are different models and columns are different websites on the internet, right? And I'll get a log loss number or log likelihood number for each entry in this matrix. And then I have, the downstream performance for each of these models, and I can regress from log loss onto downstream performance, right? This is a very simple regression problem. We use a very particular kind of a regression model called a single index model. But the point here is really conceptually this is very, very simple. And the key thing here, why this is an okay thing, right? Like why am I regressing log losses onto downstream performance? You can show in a very, very simple way that if you can fit this single index model and you can find non-negative weights that make this regression model work, then what you can show is actually training directly on the weights, sampling pages proportionally to these weights is actually a really good data selection policy, right? And one way to think about that is to say, what I found is a way to weight my log losses across different websites to closely match my downstream performance, right? That's what this regression is doing. And if I can do that, I might as well train on those log losses because that's probably also going to optimize the downstream performance, right? So this is just like a very simple idea that turns out to let us really directly select data using publicly available models. No model training required. It's a very nice thing that we can do. Don't know if anyone has questions here. Happy to answer any algorithmic things before I just kind of move on. Okay. Cool. As an algorithm, it's very simple. I feel like maybe, when I'm talking about single index models and whatever, you might get sort of lost or confused or lose interest. But really, if we just think about what I'm like actually mechanically doing, it's incredibly simple. All I do is I measure log losses on websites. I look at the websites that have the highest correlation between log likelihoods and downstream benchmarks. I sort all the domains from most to least correlated, and I select them in order. This turns out to be kind of an effective data selection algorithm. I'm going to skip the math and the theory here, both of these slides. Okay. And so, I was saying earlier that a lot of these algorithms don't really seem to work very well in practice. And so we have to actually do our own validation, right? We have to train our own language models and show that selecting data in this way is actually a reasonable thing to do. So what do we do? Well, we estimate, our regression model, which is we call perplexity correlations, on around 90 publicly available models. We take 8 benchmarks that, work even with small models, and then we train and evaluate these models. And we're going to compare to some reasonable baselines, like, the fast text classifier or this thing called DSIR that was validated at scale. And then we're also going to compare to things like language filtering or no filtering at all, because past work showed that that is a surprisingly effective baseline. So, okay, how well does this thing work? Actually, turns out to work pretty well. So this is kind of the average performance across all the benchmarks. So this is the ranking that you end up getting amongst these baselines. Going to the left is better. So if we manually filter for the right language that the benchmark is in and also use the fast text classifier, we get the best performance, which is like 1.3 average rank. Perplexity correlations, which is the thing I was describing, requires no manual intervention and gets very close performance to that. And then all these other methods, that I talked about, they basically do, no better than not selecting any data at all. So that roughly matches, what I was talking about earlier. Looking at kind of per benchmark performance, we see basically the same story. One thing that's kind of notable here, so on the columns here are different benchmarks that we can evaluate against. Different rows are basically different methods. So, if I look at the Lambda row and perplexity correlations, that's when I run the data selection algorithm with Lambda as the target. And really one of the notable things here, if you look, is that when we target the English benchmarks, they are really selecting almost entirely for English. When we select the multilingual benchmarks down here, actually they don't remove English because there's a lot of high quality sort of like transfer from English domains onto non-English domains. So you can kind of see all these sort of fun things happening. Another thing that I think is a kind of useful observation if you're working with language models and doing evaluations is actually, log likelihoods, so like log losses of these models on different web crawl data is often highly correlated with downstream benchmark performance, right? I think when you first start working with language models, you think, oh, you train these models to like predict the next word, right? And you have this like log loss objective. And what you want to do is like QA. And those are very, very different things. They're like, worlds apart. But you can show like, PIQA, which is a common sense data set. On the x-axis here, this is kind of the actual benchmark performance. On the y-axis here, this is kind of how good we would predict that model is based on their perplexities, right? Their log likelihoods on different web pages. And so what that means is, if you can predict, the next word on web page as well, that's on the y-axis here, then you can actually, know how well it will do on the downstream benchmark. And that's a surprisingly good correlation. The final thing I want to talk about for this set of results and this set of approaches is kind of, I was talking about this big matrix that we do regression on, right? Where rows are different models, columns are different websites, and each entry is the log likelihood that a model attains on that. And if you think about it, I can do things like PCA or TSNE on this big matrix to try to understand like, oh, can I like visualize pre-training data and understand, which things are important features in pre-training. And we see really two very salient features, I think, that are useful to know about. The first thing is language effects. Language effects are incredibly clear-cut when you do any pre-training data work, right? English looks totally different from, French or Spanish or any other language. And so when you try to visualize any of these like log likelihood matrices, you immediately see clear clustering between English and non-English and other languages. We also see really clear differences in the difficulty of the web page, like the entropy of the website. And that's another thing that really clearly shows up in all of these kind of data-centric analyses. So if you're thinking a lot about, okay, what are the ways in which pre-training data is clearly different, language and entropy are two really core ones. Okay, and the final thing that I'm kind of excited about, I've snuck this in there even though this is much less course material and much more, research talk material, is thinking about like how do we know that the research conclusions we reach are valid, right? Like I think this is a really difficult problem in machine learning and LLMs and so on. We can't really necessarily trust any of these results, and you shouldn't necessarily trust me when I come up here and tell you great results, right? Like, well, many of the past results haven't held up. I'm doing these experiments at small scale. It's n equals 1. And so I'm trying a variety of different things, but one thing I'm excited about trying recently is to think about pre-registration, which, if you've been in a psych class or a social sciences class, has been a really popular approach. You basically declare on the internet or publicly, I'm going to run this experiment before you run it. and then you just commit to releasing the results no matter what you do. And so we're actually in the process of doing this now for this class of algorithms where we're basically scaling up about 100 times in compute, and we've kind of pre-registered the experiment we're going to run, so we don't really have the ability to, essentially fudge the results, right? Like we have to run the experiments we said, and then we have to report the results regardless of outcome. And we did a similar thing for a past work that we recently released a couple of months ago. This is a slightly different flavor result in which what we were trying to do was to predict essentially capabilities of language models on complex tasks like, let's say, being an agent and solving software engineering benchmarks. So those are very complex tasks. And you might wonder, how well can we predict how well a model does on these complex tasks on the basis of much simpler tasks, like answering questions? Turns out benchmarks are very, very correlated, and you can very clearly predict even the performance of models on the hardest of benchmarks, like things that people call emergent, you can easily predict using simple regressions. And so we did a similar thing where we first fit these regression-like things. We pre-registered predictions for really large-scale new models, and then we basically tested our approach. Turns out our predictions remained accurate even for the new Llama 3 models, which was really cool to see. So that was pretty exciting. Sorry, that was a bit of a digression. But to take away here, right, one of the two sort of important pillars, or a important pillar now, is data selection for pre-training, right? Like if you take away one thing from this talk, it's kind of pre-training data, very important, right? And data selection is kind of the core algorithmic piece of that. And what we've done is try to reduce it to a much, much simpler problem, which is fitting regressions on publicly available models. And I think there's lots of ingredients here if you're interested in pre-training research or pre-training approaches. I think there's pretty interesting ideas here about, okay, what we're going to do is we're going to fit regressions to losses, or using small-scale validation and pre-registered scaling studies. Okay, if there's any questions there, I'm happy to stop because I'm going to talk about something pretty totally different in a moment. Yes?
So are you still using all your pre-trained data, but just weighting it differently based on how those selected models?
Good question. And in fact, in some ways, that's a great segue for the next part. So one of the, I think, mindsets that's useful to get into when you think about pre-training is to think about what is the resource constraint at play, right? And right now, almost for, I think, literally for everybody, they're compute constrained, right? Your constraint is you have more data than you can train on, but you don't have enough compute to train on all of it, right? So you don't want to weight the data, because to weight the data, you have to compute the forward and backward passes. You just want to select data, because then you don't have to do any gradient steps on those. And so everything we do is, in that part, is data selection. And then the second part that I want to talk about next, actually, that's thinking about a very different regime. That's thinking about the data-limited regime, where in some distant future, we have more compute than we know what to do with, but the internet data is finite. So how do we deal with that, right? That's going to be kind of the second theme of the second part of the talk. Okay, cool. Then I will keep going. So the second part here, I've already given you the teaser, but I'm not going to be selecting data, because selecting data is really the game that you play when you're compute bound, right? When you can't train on everything. But you might be in a regime where you can train on everything. Maybe that's because what you want to do is update the model for a small niche domain where you don't have much data. Or we're thinking about the distant future in which we have a million GPUs and we can train on whatever we want. So we know that language models struggle when there's not enough data, right? Language models have this big data efficiency problem. But so far, I think no one really thinks about it because we're not data bound, right? We can keep training on more data, so data efficiency just doesn't seem like a big problem right now. But really, this is going to become a problem as we start to either exhaust data or we start to think about more niche domains. And we do know that if we want to make a model work well in some area where there's not that much pre-training data, there's tried and true techniques for doing it. It's called continued pre-training. There's been a number of papers. Here's a random small selection of successful continued pre-training papers that adapt these models for things like law or math or medicine or whatever. These models generally work well. The math models being and code models actually being regularly used in a variety of downstream applications. But if you look at this table and you really want to apply this kind of technique to make your model good at your own domain, you start to see something very disturbing, right? On the right column, right, the number of tokens that you need to run continued pre-training, that's like 15 billion. To be safe, you probably want 50 billion tokens, right? That's a ton of domain-specific tokens that you need in order to make your model sort of smarter in a domain. And realistically speaking, we do not have that many tokens. If I want to teach a language model to know, I don't know, Stanford's like administrative policies really well, you do not have that many domains or that many tokens. And so, one thing you can do, of course, in that regime is you can like build a RAG system, and this is kind of the stuff that you've learned about with grounding and so on in the course. But I want to maybe, for the moment, bear with me and talk through an entirely alternative, much more inefficient approach, right? What I'm going to try to do is I'm going to start with 1.3 million tokens, way too few to do continued pre-training directly. But I would like to come up with a new, more data-efficient algorithm that lets me put the knowledge in these books into the parameters of the model, right? So this is continued pre-training with 10,000 times less data than sort of what people have been doing before. So let's think about that, sort of why doesn't this work, right? So standard pre-training and standard continued pre-training, both of these approaches, do the well-established pre-training playbook. What is that? Well, you have, a piece of text, in this case, the abstract to my paper, and, you're going to take as input some prefix, and you're going to predict, what comes after it, right? We all kind of know this. But the issue with this, if you think about it for a little bit, is what are we learning? We're learning to predict what comes, to the right. And this is a really data inefficient way to learn. And people have talked about, something called the reversal curse, which I don't know if you've covered in this class. But it's a phenomenon that basically says when you're trying to sort of query the model for knowledge that's stored in the original direction of the text. So in this case, let's say, I ask, what does synthetic CPT do? This is a very easy task because in the prefix, I have the word synthetic continued pre-training. In the suffix, I have a definition of what that is, right? So this first question is very easy. The reverse question actually is very difficult. If I ask like, what is a technique that synthesizes a large corpus artificially, right? Now I have to start with the thing that I predicted and then map that to my inputs, right? I'm going from like y to x rather than x to y. People have shown basically that if you are querying the model in this kind of reverse direction, performance degrades very dramatically, right? So that's one evidence that these models are way less efficient than we are as humans at learning from text, right? And so, let's think about this for the moment, right? Like we know that continued pre-training, this approach of like doing a single pass of, autoregressive training on a corpus does not work very well. We do, however, know that pre-training works, right? That's how ChatGPT is made. And so what's the difference here? Well, the key difference here in some sense is the diversity in which we present the same fact, right? On the left, if we look at continued pre-training, let's say I have a single book, I only have one instantiation of that book. There's only a single, instantiation, a single presentation. Very not diverse in a way, right? On the other hand, in pre-training, if I want to learn about linear algebra, there's a ton of different places that are talking about, the singular value decomposition, right? Probably there's a Stack Exchange post, there's a Wikipedia post, there's some Reddit discussion, right? There's hundreds of different ways in which the same fact is going to be rewritten. And in some sense, that's really critical for language models to learn, given the way in which they're trained, right? And so, I told you earlier in this talk that I am not going to do anything sophisticated at all. And so I'm not going to do anything sophisticated. All I'm going to do is I'm going to take my continued pre-training data. In this case, let's say it's a single book. And let's say, hypothetically, that I could take the single book and I could rewrite it in, millions of different ways. And I could rewrite it in ways that look like Wikipedia or Stack Exchange or Reddit or whatever, right? I can emulate what this piece of text would look like if it was a whole bunch of internet websites. Let's say I could do that, right? If we walk through that thought experiment, then in some sense, conceptually, this is going to be identical to pre-training, right? Like there should be no difference between pre-training and this sort of weird augmented version of continued pre-training that I'm doing. And so that's kind of the goal here. I'm going to try to, in some sense, replicate the diversity of ways in which knowledge is presented in pre-training in the hopes that that will give us something interesting out at the other side. And so I would like to vary kind of the content, like what is the, each website talking about. I'd like to ideally vary style, like how it's presented. And then this will give us a lot of data diversity that will hopefully let us generalize. And if you followed any kind of literature on synthetic data or model training, this is pretty different from, I think, how many other people have been taking a approach on synthetic data. Some people have been doing synthetic data for compute or size efficiency. So that's, if you're familiar with what Microsoft has done with the Phi models, that's exactly this. Others, including myself and my lab, have done like fine-tuning work where we generate instruction tuning data using language models. So this is different from either of those. Really, our goal is to just increase the diversity of data rather than fine-tune it or to make the size of the model smaller. Okay, maybe this is a good stopping point. If anyone has questions, feel free to ask them. Okay, or not. So I think with all machine learning things, one of the core challenges is how do we do evaluation? I think the pitch that I gave you for, okay, I'm just going to rewrite this book, I think that's conceptually appealing, but we have to be able to evaluate it in this very rigorous quantitative way, and we have to ideally evaluate it without using too much compute. And so there is actually a very nice data set, or more generally a data set construction strategy that works pretty well. So the idea here is I'm going to take a reading comprehension data set, in particular a reading comprehension data set that's designed for long context, right? So this has very long books, and I would like to have question answering questions associated with these books. And there's exactly such a data set called Quality, published by some folks at NYU and Anthropic. They basically took a bunch of somewhat obscure public domain books that most language models don't really know very well. Knowledge, here in this case, like kind of appears once or twice in the pre-training data set, and there's high quality human written QA evals that are written against these books. And so, Quality fulfills all of these criteria. It's niche fiction, it's fairly small amount of tokens, and there's high quality QA and summary evals. Just to contextualize performance from when I start to talk about some of the results, GPT-4 on this data set achieves 51% accuracy. Random guessing is 25%. And so clearly the models know something about these books. It's been trained on them, of course, but nowhere close to human level accuracy, which is like in the 97 or 98 or something. If you put the book in front of people and you ask, it's in like the high 90s. Okay, so how can we teach a language model the contents of these books, right? So that's kind of the question. Or it's a toy problem, but that's the problem I'd like to solve. So the very first thing I'm going to do is I'm going to do just continued pre-training. This is the thing that I told you about before, right? I'm going to take all the books, and I'm going to train my language models in the usual autoregressive way. Next word prediction, I'm going to run through all 1.3 million tokens or so. Now, so if I show you, what happens, Llama 3AB, which is the model that we're going to be improving, that's the black dashed line. That's kind of the baseline from which we start. If I do this continued pre-training approach, that's the green line over here. It actually does worse than the original model. Any non-trivial amount of continued pre-training actually makes the model worse, because not only is the model not absorbing the knowledge, in some sense, we're also destroying its ability to follow, good instructions. And so, it actually does worse. GPT 3.5 and 4, they're slightly higher up in sort of this plot here. As I said before, it's about 51% performance with GPT-4. So one of the things that I can do, this is slightly inefficient in terms of, the cost to generate the data. But let's say I take the books, and I do kind of the simplest possible way of making the data set bigger. I'm going to call the OpenAI API, and I'm going to ask it, okay, here's the chunk taken from a book. Please rewrite it. Just like paraphrase it in whatever way you want. Just rewrite it in many different ways, right? So I'm just going to rephrase that book. And that's going to give me this blue line. As I generate more and more synthetic tokens from rephrasing, I actually see pretty predictable linear gains. If you've seen many different kinds of language model training plots, some people would call this a scaling law on this sort of y-axis here. And that's kind of exactly what you want to see, right? In some ways, the success of modern language model pre-training, that's predicated on a scaling law. Once you start to see predictable improvements in performance from resource inputs, if it's economically valuable enough, you basically throw GPUs at this to make performance go up, right? But unfortunately, performance goes up pretty slowly with rephrasing. We're barely beating GPT 3.5 in this plot after, I think, like 50 million tokens or something like that. And so that's not really great. And so we would like to ideally be more efficient, more token efficient than that. And so here is like a general, not tip, general successful approach in synthetic data generation. The core problem here is that we're asking language models to come up with data or to come up with new kinds of data. But language models, especially the ones that are instruction tuned, are not terribly diverse. I'm sure many of you have attempted to use ChatGPT for your writing at some point, hopefully not for your writing assignments, but for writing. And you'll find that it's very fixated on certain ways of writing, right? It can't like generate all sorts of diverse outputs. And we've seen this both in sort of this rephrasing thing, but also in another recent work where a student of mine was working on sort of using LMs to come up with research ideas. And one thing that's very striking that we saw, this was with Claude 3.5, was as you ask the model to generate more and more ideas, it kind of eventually runs out of ideas. And after about 1,000 ideas, every new idea you're getting is almost a duplicate of the old one, right? So there's very low diversity for these models. And so because of this, a lot of really successful ways of generating synthetic data rely on an approach that I call kind of externalizing the diversity. And what that means is you have some external source of randomness, and you inject that randomness into the prompt of your language model, and that allows you to get a much more diverse output on the other side. And so to give some examples, Stanford Alpaca, which was a really early instruction tuning model we built, we have random human seed data, and we condition on the past data. So when you generate, you always sample a random set of other data you've already generated, and like try to generate something that is different from that. Some folks at Princeton came up with this approach called skill mix instruct. And in that approach, what they do is they list a number of skills that you want. They're generating data, so they're asking like, oh, here's like 10 different skills. They pick random pairs of skills and they say, oh, generate a example that requires both of those skills. And our approach is going to be to randomize over different topics that you can talk about, and we're going to do that through a knowledge graph kind of analogy or a formalism. And so, I think in a way, what we're going to do is go back to some of the early ways to think about knowledge, right? So in a document, you've got a lot of entities. These entities have relations. And what we would like is for our model to have a good understanding of all of the different relations between the entities. That's kind of the best that we can hope for. So the way that we do this is, we start by prompting the language model to generate all the entities that appear in a book, right? So we come up with a big, long list of entities. And then what we're going to do is we're going to take these entities, and then to generate a new synthetic piece of text, I'm going to sample some k random subgraph of the knowledge graph. So in this case, it's a 2 subgraphs. I'm going to pick 2 random entities in the graph, right? So I'm going to pick Da Vinci and the Louvre, and those are kind of my 2 nodes that I'm going to care about. And then the augmenter LLM, takes these 2 randomly chosen entities as input, and the prompt is very simple. It's something like, describe the relation between the Louvre and Da Vinci in the context of this document, right? And if the LM does this instruction correctly, then what it's going to do is, in some sense, it's going to traverse the knowledge graph, right? It's going to say something like, the Louvre contains the Mona Lisa, which was painted by Da Vinci, right? And so we're basically surfacing these indirect relations about, let's say Da Vinci and the Louvre. There's never a direct connection between those 2 in the document. We're going to force the language model to spell that out and then put that back into the training set of this model, right? So, to put this all together, really what we are doing is that a document, it has a lot of facts in it, right? It has a lot of implicit facts. If we read the document, we can form inferences about, different entities, and we're taking those implicit facts that are never explicitly stated, and we're sort of materializing them explicitly using the synthetic data strategy. And, it also serves as kind of a form of randomization. So what happens when we do this? Like this is an approach that my student called antigraph. This is the salmon colored line in this plot here. It scales much more nicely and more efficiently than just naively rephrasing. And if we just keep scaling to the right and the right, I think this ends at about 600 million tokens. We can pretty handily beat GPT-4 sort of closed book in doing QA. So that's actually quite nice. And I think we can hopefully continue to scale with additional token inputs. Of course, we stopped here because we weren't quite as interested in continuing to double the amount of token budget that we had. One thing that you might be concerned by is that we're using GPT-4 to generate the synthetic data, and so maybe it's just distilling a lot of knowledge from GPT-4. And so we checked against this by saying, okay, like how well do we actually do relative to GPT-4? And we improved significantly, like 17% via Antigraph, which once again exceeds GPT-4 by a decent bit. And I think the reason why this approach is very exciting to me is because what I would like to do is I would like to build language models that have knowledge in a very specific domain. Like I want to build language models that can help us do research. To do that, they need to have a good understanding of scientific knowledge. And when we fine-tune these models, like these continued pre-trained models using instruction tuning data, we actually see lots of multitask behaviors that we see with things like ChatGPT. Like we can ask the language model to brainstorm, or not brainstorm, like give a list of how the practice of dentistry in the US has changed, and it will give you a list using facts from the documents. Or we can ask it to compare two different articles in the set of articles, and it can do that as well. These were never really explicitly in the training data, and so that's very encouraging to see, right? That we can do things like summarization or relate multiple articles in this very general way, despite only being trained on task-agnostic data. When we look at summarization, the model, without looking at the books at all, right? This is all closed book evaluation, can do summarizations of books. We asked, in this case, like, what is the book Cosmic Yo-Yo about? It can nicely summarize that. Other baselines, don't basically have the knowledge to summarize this book. What I've highlighted in red here are hallucinations, right? So continued pre-training with our approach, gives dramatically better hallucination rates for summarization. And when we evaluate quantitatively using GPT-4 itself to evaluate, how factual is the summary, how salient are the claims that are being made in the summary, the salmon-colored one, which is Antigraph, once again does really well. It makes very few hallucinations while making claims that are salient, comparable to sort of humans. The x-axis is salience here, and the y-axis is in some sense hallucination rate. The same is true even when we carefully match total number of tokens and when we generate total number of synthetic tokens that we use to do this evaluation. So, okay, kind of the final thing that I want to sort of, in terms of the empirical evaluation that I want to talk about is, all right, so you've been talking about spending lots of money and lots of GPU time to generate synthetic data to put knowledge into a language model. But why wouldn't you just use a RAG system? And this is a fair point, right? Like I think if you want to build a system today, you're obviously going to build a retrieval augmented system, right? But I think one of the things that's quite encouraging to me is that when you build a system that has more, domain knowledge, turns out that you get, benefits on top of RAG. And in this case, we built a RAG system that is incredibly accurate. So if you look at the recall at 8 number here, one of my students, Neil, I think he dedicated 2 weeks of his life to just making a really good RAG system. And within the top 8 articles, 99% of the time, the right article is in there, right? So it's very, very accurate in terms of the retrieval accuracy. And even against this strong baseline, if we apply continued pre-training, we still see 2 to 3% gains on this, which I think is actually quite encouraging. It means that, even when the retrieval is near perfect, there's still a lot of room for improvement from just doing some simple domain-specific continued pre-training, right? So, and another sort of way to contextualize this is to say, the closed book performance that we got, right? This is without any RAG system, 56%, is almost as good as the Llama RAG performance, and it's 80% of the gain, 80% of the way there from retrieval, which is quite nice, I think. So the final thing that I want to talk about today is to think about, okay, I think synthetic data is a kind of interesting space because it's also accompanied by a lot of hype, right? In some sense, when people talk about synthetic data, they're like, oh yeah, this is going to solve all of our data problems. We'll just generate data out of thin air, and we will no longer have to think about things like data limits. But I think this is not the case. So I think we need to think very carefully about what is synthetic data buying us, what is it not buying us. And so one of my students, Zitong, and Xuanping, who was a collaborator, sat down to try to think about, okay, like what's the theory behind synthetic data here, or at least our synthetic data augmentation. And so why do we get gains from rewriting the same piece of data in many ways? So what we did was we built a simple toy mathematical model. Let's say we have a set of V different entities in a single document D source. And this is your knowledge graph that we talked about before. And within this document, there's going to be a bunch of claims that appear directly. By directly, I mean things like X is Y, or like Tatsu is teaching, right? Like these very direct statements are direct edges in the graph, right? And we're going to assume that, just for mathematical convenience, that this document graph is just going to have a random graph structure. Erdős-Renyi graph where you just flip a coin for each edge, and that's going to determine whether that edge appears, right? And one thing that we can show is we can very precisely analyze the process that we have of saying okay, what does synthetic data do? Synthetic data is describing the relation between two entities that may not necessarily be directly in the document, right? That's kind of what we're doing. We can formalize that very precisely as mathematically and say, okay, what's happening is we're going to follow this knowledge graph path, and then we're going to fill in the edge that didn't used to exist. And the salient question is, what can we possibly know about the entities? That's going to turn out to be a mathematical question equivalent to saying, how much can we fill in this knowledge graph given a partially filled in graph and the ability to connect any two sort of nodes that are sort of within the same connected component. And you can give a very precise description. I'm going to save you from having to look at the asymptotics, just to say basically there is a fairly clean sort of final result that says, if our graph is all fully connected, then that means that the document has the knowledge to describe all the entities. Then synthetic data can sort of get us all the pieces of knowledge in the document. Otherwise, if there's entities that are not described at all in the document or not connected in any way, then those don't get filled in any way. So it's in some sense an obvious statement. But one thing that's kind of nice is it does fit the empirical observations that we had in terms of how performance improves as a function of the number of synthetic tokens. So if we take that formula and we fit it, we see fairly nice sort of clean empirical fits with respect to sort of the performance of this curve. So okay, the takeaway here, I think, hopefully this was kind of interesting given that, in a lot of the class you've been learning about grounding and how to put knowledge into language models. I think the perspective here is to say, not only can we, put knowledge in by prompting and these post hoc approaches, we can really start to inject, domain-specific knowledge deep within the parameters of a language model. Of course, the cost here is that we are spending a ton of GPU time generating synthetic data and doing the equivalent of pre-training, again, on a particular domain. But really, the top-line conclusion here is that, pre-training isn't restricted to pre-training. We can use the same playbook to improve knowledge of language models on a particular domain. And we can make it effective at the really tiny 1 million token level. And we can get a model that's almost as good as a retrieval-augmented model without having any retriever, which is kind of surprising. And if you're really interested in kind of pre-training data efficiency research, I think one thing that I didn't talk about, but I'm personally really excited about, is that this setting of doing continued pre-training in a data-efficient way is also a really good kind of toy model for thinking about the future of language modeling, where we're going to eventually run out of high-quality internet data, right? When that happens, we're going to have to rely on techniques like this to effectively get more data-efficient ways of learning from the same number of tokens, right? So I think this is a really interesting place to kind of mess around and do algorithmic development and think deeply about how do we make these models work? Okay, so to wrap it all up and to put things together, right? What I wanted to talk about today was kind of the central role of data and how we can algorithmically intervene on data in many ways, right? And the place at which I'm going to intervene is on this kind of pre-training style training, because that's the place at which we can deploy the most compute, and that might have the greatest amount of leverage. I think my perspective here is kind of the opposite of many of my academic colleagues. In some sense, pre-training, very compute intensive, but also maybe the most exciting place to be doing algorithmic work because it has the greatest leverage. So the first part was kind of about data selection, and that was basically saying there's this big wealth of information, which is models other people have trained, and we can use that to try to understand what does high quality data look like. And there's some promising signs that that's possible. In the second part, I was much less talking about the compute bound setting, but much more the data bound setting. And there, synthetic augmentations and thinking about, continued pre-training allows you to build models that without using a retriever or any kind of external augmentation can do really well in answering, narrow domain specific questions. So that's kind of an exciting, potential new direction, coming up. So, thanks a lot. If you have any questions, I'm happy to take them. Yes.
I'm actually a psychology major. I study neuroscience and also I'm doing classical memory right now. And it seems that for humans at least, the strategy is when you study to form these connections. You want to get topics and see how they once you link your topics to your overall knowledge, it's a lot more effective than just reading the textbook.
Right.
And are we seeing this play into effect why the knowledge graph is a much better data set than just naively picking data? And are there any other ways of potentially augmenting data to be more like how we train?
Yeah, I think that's a very interesting question, and I think I'm still pretty on the fence about this in some ways, about whether the human learning analogies are relevant or useful for training language models. On the one hand, I think we can think about curriculum and how to present knowledge to models in a way that's more easily learnable, inspired by human learning strategies. And I think that's pretty interesting. On the other hand, we do know that when we do one pass of continued pre-training, for example, models are infinitely less efficient than humans, right? I look at a textbook chunk, I'll roughly understand all the facts and their implications. You do one pass of autoregressive modeling on a text chunk, models are going to understand 0% of what happened there, right? And so I think there's this question of do we need a new algorithm? Does data augmentation emulate how humans learn? How do we close the gap? I think those are very interesting questions. I just don't know what the answer is. What I do know is, one pass training is very different from humans. So maybe when we close the gap, they will become similar. Yes?
You mentioned the goal of a lot of frontier researchers is to create new knowledge, and with the empty graph framework, do you think of that as creating new connections, or is there a better way to think about it? Or
yeah, that's right. I think, I'm deeply skeptical of any kind of arguments that you can create knowledge with synthetic data. That just seems fundamentally really difficult. I think about kind of two different things. One is text is often a manifestation of interactions with the real world, right? The grounding. I go out and I don't know, I have dinner at a restaurant, I have a bad experience, I write about it online. That's a grounded experience that's been mapped to the internet, right? Since language models don't yet go out and have dinner, they can't possibly create this new piece of knowledge. What they can do, though, is they can look at all the bad reviews and say, actually, this restaurant is probably on average bad, right? So they can synthesize all these grounded interactions through reasoning. They can make, implicatures based on that. And you can think of that as new knowledge, but they're essentially what people might call deductive closures, right? They're logical inferences from what's already available, not necessarily materializing new facts about the world. Oh, yes.
So this synthetic pre-training to hurt the creativity or new idea generated by large language model, because I remember you have another paper talk about the research idea generated by this.
Yeah. I think kind of yes, but also maybe that's not the major factor. So when I talk about kind of diversity losses and lack of creativity of LMs, I think the biggest contributor to that is actually the alignment process. So if you look at different models at different stages of their training pipeline, the base model, the autoregressive, next word prediction model, very creative in a way. It will output all sorts of crazy hallucinated stuff, but you'll be like, wow, that's very creative. You do supervised fine-tuning, it's going to follow instructions better, but less creative. And once you do all this RLHF alignment, now you've really put the model on rails. And so I think that's where all the diversity losses come from. Continued pre-training does in broadly speaking, make language models lose their capabilities. Like they're a little bit worse at in-context learning. They're a little bit worse at basically picking the right options out of a multiple choice question. But those losses are generally small relative to the alignment tax, I guess, that you might call it. Cool. Yes.
So for our project, we're actually part of it. Like we're generating stories. We're basically continuing the generation process of a story, and we realize that the stories that's generating based on the previous plot is actually like it's decent.
Right.
It's like pretty good.
Yeah.
And I just wanted, because you also talked about how it kind of like only knows a couple of styles.
Yes.
So I'm curious about like, well, maybe we just haven't like pushed it far enough so that all the stuff is the same.
Yeah, I think maybe it only knows one thing is the wrong sort of maybe phrasing of it. It's kind of like, let's say you have a story, but you want a million different continuations.
Yeah.
That's, I think, very difficult. Like, I think models, will eventually cap out on the different ways that it can continue the same story. Whereas I think if you have many different, prefixes, many different starting points of the story, you'll get many different continuations, if you know what I mean. Like, this is what I mean by, like, externalized randomness is really important. If you change something about the prompt, you'll get a totally different response.
Right.
But if you don't vary the prompt, you'll often cap out.
Right. So it sounds like if we don't do the reinforcement, like if we just do the pre-training part,
Yes.
autoregressive, that will be very creative. So is there like a model that does that?
Well, I mean, yeah, right. Creative, I think, is a double-edged sword, right? Like, you want creativity in that, oh, wow, that's like, I didn't think of that creative. But also, total gibberish is something you haven't thought about, right? So I think there's this big balance. And in a way, there's a person here, Peter West, who's been like kind of messing around with some of this research. But in a way, alignment is really focusing towards the average case. Right? Like when you prompt a model and you need the answer to be like generally correct, you want alignment, you want boringness, you want, inoffensive but good continuation. When there's a human in the loop and you're gonna pick, the best out of 1,000 different generations, the game is very different. And the companies aren't really optimizing for the second use case. And there you might want a base model or a much more lightly aligned model. And I think those are kind of very interesting sort of, variations of this. Great. I think we're a few minutes early, but if there's no more questions, I won't keep you.